this carbon was labeled so that we could monitor it. Either it's labeled as a carbon 13, so we can monitor it by mass. Or if it was carbon 14, so that we could monitor it by radioactivity. That carbon becomes that carbon, specifically, right? There's a very, again, of enzyme-driven specificity that makes that carbon of citrate from that carbon of acetyl-CoA. So if that one was labeled 100%, all of that carbon would be labeled in the citrate that we made. Okay? So, at that point, that label is there and we can follow it. So, we isomerize, and because of the three-point connection and the, even though this is not a chiral carbon, when the enzyme creates a chiral environment, the enzyme can tell this end of the molecule from this end. And so that movement of the hydroxyl group occurs at the end away from that labeled carbon. Right? We can still tell. This carbon has 100% of the label. Right? This hydroxyl group is the one that we moved. Right? This carbon is not labeled at this point. Okay? When we decarboxylate, it's this carbon that we lose in the decarboxylation. So again, this carbon at the far end holds all the label. Right? When we do the alpha-ketoglutarate dehydrogenase, it's this carboxyl group that we lose, and the sulfur of the succinyl-CoA ends up there. So still, if we go to the far end, all of the label is there. Right? The problem is, once we get to here, to succinate, we have a molecule that's not chiral, and it doesn't have a structure like this where it's even prochiral. So even in a chiral environment, these two ends look identical. And so because the molecule now can flip-flop in any enzyme it interacts with, where we can say all the label was always found here, now the best we can do is say, if we happen to grab one end or the other, we have a 50% probability of that one being labeled. Does that make sense? And so that is true the rest of the way through. Does that make sense? So, what now? We have to reorganize. Yeah, succinate dehydrogenase. So we'll talk about succinate dehydrogenase. Succinate dehydrogenase is an oxidation. What are we going to use as the oxidizing agent? FAD instead of NAD. Why are we going to use FAD instead of NAD?
One at a time.
What? It can move one electron at a time. Also, what's NAD good at? Oxidizing?
FAD.
Yeah, it's good at oxidizing FAD. It's also good at oxidizing hydroxyl groups. Do we have hydroxyl groups here? No. So the other thing FAD is good at is oxidizing saturated carbons, especially when they are next to a carbonyl. Right? So here we go. We've got saturated carbons next to a carbonyl. That's one of the things FAD is good at. Okay? We won't talk about the mechanism of this one, but trust me that that is the case. So since we're doing this chemistry next to a carbonyl, what is probably involved? Carbanion. So we're going to create a carbanion and then transfer 2 electrons as a hydride ion into subsequent illumination. So again, right, we take advantage of FAD's flexibility here. So with succinate dehydrogenase, we use FAD as the oxidizing agent because we're oxidizing this saturated carbon. And it specifically gives us the trans stereochemistry of the new carbon-carbon double bond, and that we call fumarate. So one distinction we have with succinate dehydrogenase is that it uses FAD as the oxidizing agent. What's the other thing that makes succinate dehydrogenase different from the other enzymes of the citric acid cycle? Well, where are the enzymes of the citric acid cycle?
Mitochondria.
Where are they?
Mitochondria.
Where in the mitochondria? Where in the mitochondria are we working? Where are we in the mitochondria? Yeah?
The folds.
In the folds? Well, that's actually not a bad answer. Where are we?
Matrix.
In the matrix, right? So we're in the matrix space of the mitochondria. And the matrix space is a soluble fluid space. And so most of these enzymes of the citric acid cycle, all the ones we've talked about, are soluble enzymes of the mitochondrial matrix. If we isolate mitochondria and disrupt their structure to release those enzymes, they are released as soluble enzymes in solution, right? But succinate dehydrogenase is not released. If you disrupt mitochondria and isolate the membrane fraction, then that isolated enzyme mixture loses the ability to complete the citric acid cycle. And what builds up is succinate, meaning something about succinate dehydrogenase is dependent on the membrane fraction of the mitochondria. Okay? Well, what we find then is that succinate dehydrogenase is not a soluble protein of the matrix, but it is an integral protein of the mitochondrial inner membrane. Right? And it is, why am I having trouble talking today? It is directly associated with the proteins of the electron transport chain. So succinate dehydrogenase interacts directly with the electron transport chain. And we'll talk about that more when we talk about electron transport.
Is that why the FADH goes to a different part? Like, with the electron transport chain? That they always told us that NADH starts at a different spot than the FADH does?
Yes. That's one of the things. What we will find, just as a preview, is the NADH Q reductase, the enzyme that actually oxidizes NADH. What does it use as a coenzyme? FAD. Right? It uses FAD as a coenzyme, or at least a flavin. And so it takes 2 electrons from NADH so that it can reduce coenzyme Q. Succinate dehydrogenase that already has the electrons in FADH2 can directly reduce coenzyme Q. So we'll see that connection when we talk about electron transport. Okay? Question, Michelle?
Maybe.
Okay.
But is FADH then a control factor of like the getting through all the way through the citric acid cycle? Because it must be reoxidized before it can take on another catalytic cycle?
Yes. So, but remember, what's different with FAD as a coenzyme compared to NAD? And this is a hint.
Bound.
It's bound to the enzyme, right? So this is where, when FAD is reduced to FADH2, it's not, an NAD using enzyme can release an NADH and bind a new molecule of NAD. But an FAD using enzyme, when it is reduced, what's its only choice?
Oxidize.
It has to oxidize that one to do it again. And where does that get oxidized? Electron transport chain, right? So this cycle is dependent, where it is related to control, it is dependent on the electron transport chain being active. So if the electron transport chain is backed up, if FADH can't be reoxidized to FAD, then the citric acid cycle will get held up there because succinate dehydrogenase won't be able to work. Does that make sense? Any questions about that? Huh. On that, we're out of time. We're almost back around. We've only got 2 steps and we're done. No questions? Okay.